Good afternoon, everyone. Thank you so much for joining us on the second and later half of the day for TMLS 2020. I have the distinct pleasure of introducing something that just sounds cool to introduce because our next speaker, Shreyansh Daftry, works at NASA, which is pretty cool. So whenever we have tough days and we talk about, well, you know, at least it isn't rocket science, I don't know what you have to say. I'm curious. When you have a day where you're like, it isn't rocket science, you can't really say that because every day is rocket science, because if I understand, you work in the Jet Propulsion Laboratory, which is really, really cool. Shrey is a research scientist. He's working at the intersection of artificial intelligence and space technology to help develop the next generation of robots for Earth, Mars, and beyond. Definitely want to know what beyond means. He's got an MS degree in robotics from the Robotics Institute in Carnegie Mellon University, and his BS's degree in electronics and communications engineering at the Manipal University in India. His research interests span computer vision, machine learning, automated robotics, with a focus on real-time computation, safety, and adaptability. It's a lot of syllables, so hope I got that all right. He's received numerous awards and honors, including the NASA Space Act Awards and the JPL Software of the Year Awards for his contribution to the fields of space and aeronautics. So very, very excited to introduce our next speaker. Really looking forward to his topic on how machine learning is being used in space exploration. Over to you, sir. Let's hear what you got to teach us.
Thank you so much, Stuart, for that grand introduction. And thank you for all the organizers of TMLS for organizing such a great event. Let me start by sharing my screen. Okay, so hello everyone. My name is Shreyansh Daftry, and I'm a research scientist at NASA's Jet Propulsion Laboratory. It's my honor to be here, and in today's talk, I hope to share with all of you my excitement about how the use of artificial intelligence and machine learning is enabling new frontiers in space exploration. Just a note on the talk, so I've made the slides here in a very high level manner. So it's more of discussing how we're really using machine learning and presenting some examples, case studies, and videos of what we've been doing with that. I don't go much into technical details in depth. So if any of you are interested in exploring more, shoot me up and we'll be happy to take the conversation offline. So NASA, as we all know, has a long history of building really capable machines. For the last 60 years, we as an agency have built spacecraft that have visited almost all the objects in our solar system, from the moon and Mars to the outer planets like Jupiter and Saturn. To the extent that two of our spacecrafts, Voyager 1 and Voyager 2, as illustrated here in the picture, have been the first man-made space objects to reach interstellar space. Growing up as a child, this inspired me, and that's always what I wanted to do, become a robotics engineer and build intelligent machines for space. But as I started to learn more, I understood that while NASA has been building really capable machines, they're not really what I as a trained roboticist would yet call intelligent. Here you see two of my favorite pictures. On the left is a picture from the Apollo missions, which carried the first humans to the moon. Now, one of the most critical aspects of that mission was the final landing. And that was made possible only due to the sheer intelligence of the human astronauts themselves, who manually piloted the aircraft for a safe touchdown, an extremely complex maneuver that is to date still difficult for machines to accomplish on their own. Similarly, on the right, you have the picture of the Curiosity rover on Mars. While the rover is one of the most capable machines ever built that I'm aware of, it is remotely operated by a large group of humans from the mission control room here on Earth. Every day, a team of scientists and engineers uplink a detailed sequence of actions, carefully planned for the rover to perform. This has been the typical way NASA has operated and developed missions in the past for the last 60, 70 years. While this has worked so far, it's definitely not scalable for future missions. There's a growing need for future spacecraft to be autonomous, self-aware, and the ability to make critical decisions on their own. This is primarily driven by two major factors. First is the difficulty of deep space communication. Apart from the fact that we are severely bandwidth limited, we don't have extensive space internet, these planetary bodies are just simply very far, as you can see here in some of the numbers. The next few decades of space exploration is going to be involving visiting the outer planets, and this is what I had meant by the moon, Mars, and beyond, like Jupiter's moon, Europa, which is considered to be one of the best places in our solar system that might have evidence of life. For Europa, it takes several hours for us to send a signal and receive it back. So the only way we could send robots there is if they are fully autonomous, period. The second major reason is scalability. The image on the left here is a snapshot of all the satellites in orbit around Earth at any given time. And this is a few years old itself, with exponential growth every year happening with commercial space interest. On the right, what you see is a vision of what Mars colony might someday look like. Now imagine having a team of 100 plus engineers and scientists sitting here on Earth controlling each of those single assets. It's just impossible and unscalable. The only way we can scale up the space economy is if we make our space assets to be self-sustainable, and artificial intelligence and emerging technology like machine learning is a key ingredient in making that happen. So how would an AI-powered space exploration look like? To understand that, our team first mapped a few key areas for planetary robotic mission where machine learning could make a 10 times difference. These are autonomous navigation, think self-driving cars on Mars; autonomous science and planning, how can we use artificial intelligence and machine learning to do better mission operations, automated scheduling and planning; precision landing, as I was motivating in the Apollo missions. Think of an autopilot that helps our spacecraft land safely to its desired target location; autonomous manipulation, allowing our rovers to not just move from A to B, but also do intelligent behaviors like picking up objects, keeping them, performing sampling operations, etc. And finally, what gets me most excited is successfully being able to work in teams someday along with human astronauts. Said that, I would like to mention that in general, there is a wide range of applications in space exploration beyond robotics and autonomy, where machine learning can be very useful. But that's beyond the scope of the work that I and my group does. In this talk, I'm going to focus on one of the capabilities, autonomous navigation, and more specifically talk about two projects that we have been recently working on. The first one is machine learning-based semantic perception. And the second one is machine learning-based motion planning. So let's talk about the first one. For more than 2 decades, we have been proudly operating rovers on the surface of Mars, doing autonomous navigation. Our top, and this is what's, I'd like to almost say level 5 autonomy per se, just that some things are much easier and some things are harder. Our top priority, of course, which makes things hard for us, is of course always safety. So how do our rover planners navigate the rovers in a safe manner? That largely depends on images that we get back from the rovers, both from the orbit and the rover itself. For example, on the left, you see an example image from the navigation camera of the MSL rover, which stands for the Mars Science Laboratory, or its nickname Curiosity. And on the right is the orbital image from where our next rover, Perseverance, which will be landing there in February 2021. Now, when a human rover interprets the images they use to decide plans for rover's navigation, they use two kinds of information: geometric and textual information. The geometric information maps to the surface topography. For example, on the left, you see the local topography of where slopes are, where the obstacles like rocks and outcrops are. Similarly, on the right, you can see more of a global topology like mountains versus dunes, etc. In contrast, the textual information maps to semantic information. The textual information maps to semantics like terrain types. For example, on the left image, you can see that the regions of the image labeled as soil versus bedrock. Both geometric and textual information are crucial for safe rover navigation. However, our rovers so far have only been seeing the world in this way, which is geometric. The current onboard autonomous navigation system called AutoNav only uses geometric information like planar information, where the rocks are, obstacles are, to do traversability analysis using geometric stereo processing. The ground software too could only process topographical information. So we've done quite a bit of navigation like this, but what could be the danger in driving this way? For example, we lost Spirit rover in sand. The Opportunity and Curiosity rovers nearly got stuck. Telling sand from cohesive flat surface is not possible without textual information. And this is something humans do just using their brains right now and using past experience. We don't have very good models still of how the Martian soil would look like and behave through vehicle-terrain interactions. So making these kinds of decisions on the fly, especially for long-term autonomous operations, is extremely crucial. And if something we've learned over 2 decades of driving on Mars is that this is the top reason why we could potentially lose $1 billion mission. So in response to that, we created Spock, a deep classifier for Mars rovers. With Spock, autonomy algorithms can see the world like this. Just like humans, Spock can tell the terrain types on image based on textural features. We developed 2 versions of Spock, one that works on the rover and uses 6 different terrain classes as shown on the image on the left, and one that works on orbital images and has more fine-grained classification that uses 17 different classes. In summary, with Spock, we have made an attempt to enable a human-like ability for algorithms to assess the traversability and safety of rovers based on topography and terrain type. Our capability is firmly built upon the ongoing revolution in computer vision, deep learning, and AI in general. In the recent years, there has been great progress in the development of deep convolution neural net models for the purpose of semantic segmentation and image classification. These models typically digest an input image and output a segmentation mask with the same pixel size as the original image. We adapted these state-of-the-art models for our use case. But these models, of course, are originally intended for classifying objects on Earth, not Mars. So what we did is, as called in the field, transfer learning, meaning that we fine-tune these models with additional training data on Mars images to a network that is pre-trained by common objects. Adapting these models to work reliably in Martian terrain, however, is not trivial. And this presents a major challenge, or rather a set of challenges as highlighted here. They are data, severely limited onboard computation, and finally doing system test and validation to gain trust in these systems. So first, let's talk about data. Like all machine learning practitioners would know, having high quality data to train your models is always key ingredient for getting high performance. For Mars, this problem becomes exponentially hard because we did not have any labeled data set to start with. And the fact that we only have about 24 geologists in the world who have comprehensive knowledge about Mars to create these kinds of labels, you can only imagine how hard it is to get their time and how expensive it is to get their time to actually do manual labeling. Imagine asking one of those to actually label everything per pixel here. It would be thousands and thousands of dollars per person per minute. So this is an extremely expensive endeavor. So how do we get our data set for additional training? We've used multiple ways. We did ask our rover drivers and scientists on Mars rovers to label a few amount of images, a very few 100 images with high quality labels. But to augment that, we recently started a new initiative called AI for Mars. And this was during the COVID period in the last few months. This is a citizen science project where we used free crowdsourcing from the internet community to label images seen by past and present Mars rovers using a web-based tool in over 10 plus languages. After we released the tool, we were extremely surprised by the passionate response that we received. We got more than 200,000 labels just in a couple of months from all over the world. What was particularly exciting for the team was to see was the ability to engage kids from basically grade 4 to grade 12 in this activity. We received feedback that this was very inspiring and exciting activity for kids while the school was shut down due to COVID. And this got them excited about space, AI, and STEM in general. However, there is a problem with trying to get data like this. We solved the data problem now that we have a lot of labeled data set, but our training, but as most of you would know, training machine learning models with noisy labels is a huge challenge, and it brings a new challenge, brings about new problems to us. Towards this end, we have been doing research along several ends: how to effectively clean noisy data, how to train algorithms robust to noise. There's a lot of recent literature on that, and we've been studying and actively pursuing those. And if any of you had to deal with this similar problems, I'd be happy to discuss those more in detail offline, share notes, because this is something we're still exploring and learning ourselves. Our team just finished a CPPR submission this week on this work, and we hope to release this data set for public use in general. Another way we've been starting to look into is leveraging some great development happening in the area of high fidelity simulation and generating synthetic data sets. We worked with a startup called Bifrost AI, who excel at generating perfectly labeled terrain data of using environments using 3D graphics. As you can see, the data generated is highly photorealistic and looks just like Mars. In addition, the labels are perfect and noise-free. Now, this is a disruptive in many ways because it is almost impossible to generate such high quality data with manual labeling. And this is scalable and allows us to generate as much data as we want in a relatively short time. This is preliminary work, but we are excited at the potential of what data generation methods like this can be useful for improving our deep learning pipelines on Mars. We used all this data and were able to successfully train a classifier to segment terrain types on Martian data. On the right, you see a time lapse of onboard rover images from the Curiosity rover, and on the left, you see an aligned orbital image with the top-down view of the robot's overlaid. The video was generated on a test set that the machine learning model has never seen before, and I will let it play for. Let me see. Yeah. So you can see the diversity of the terrains that we were able to predict and the predictions that it was able to make. Based on our analysis and operations, this has considerably improved the safety of our rover for onboard decision-making and long-duration autonomy. And as a result of that, we were lucky to be awarded, this particular algorithm was awarded the Software of the Year award by NASA for 2020. The next challenge is limited computation. And this is a movie from our test of Spock Lite, which is a lightweight version of the algorithm Spock. We deployed the algorithm on our test rovers called Athena and tested in JPL's Mars yard. Spock Lite simply tells us sand from anything else. This is because it's based on a very simple machine learning model based on support vector machine. Now, while this is very simple, this is still very important because sandy surfaces, as I mentioned before, is one of the biggest hazards. At the same time, we are actively looking for a range of both software and hardware solutions to scale deep neural network to work efficiently in limited computations on board our Mars rover. Software solutions typically include techniques using simpler classical models, as shown here, model distillation, optimization in terms of compute and memory footprint, etc. We are also investigating hardware solutions like the use of AI accelerators and non-traditional embedded devices like FPGA, which are very efficient and both in terms of compute and energy to be used for our Mars rovers. Finally, the third and often the most overlooked challenge along the data science and machine learning community is system integration and end-to-end verification with the entire system. This is especially important in the context of highly complex safety-critical cyber-physical systems like robots and spacecrafts. Deep CNN models, while they work great, are inherently black box in nature, presenting a major bottleneck for system-level validation and proving guarantees. On top of that, once the rover is launched, we do not have the ability to fix things if something goes wrong. So it's pretty much one shot. You have to make it right, or you potentially risk losing $1 billion rover. So all of this results in a pretty exhaustive system integration and test campaign. I can easily spend an entire hour talking about this on how we do how we do the system testing, but it basically all boils down to recreating scenarios that we could possibly imagine to expect on Mars here on Earth and testing the heck out of the system. What you can see here is on the left is the Scarecrow rover, which is the analog version of our Mars rover that we use to deploy and test our AI algorithms. Here you see it being tested in the Mars yard on a test site on campus where we recreate terrain just like we would expect on Mars. On the right is another analog called Athena, and the video you saw was a demo, very recent demo from being able to achieve long distance driving where we drove for 1 kilometer without any human intervention. So the next project I'll talk about briefly is on robot motion planning and how we use machine learning to accelerate that. In the last segment, we talked a lot about making our rovers safer. Now let's talk a bit about making them faster. Here you see in the video is a video from a test that we did a couple of years ago on using ENAV, which is the Enhanced Rover Navigation System for Mars 2020 rover, which is now called Perseverance. One key thing that I want you to notice here is the 50 times increase in this video time lapse. So when you actually come to lab and see this rover moving, it is extremely boring just because it's how slow it moves. And this is a problem because when on Mars, if you keep moving this slow, this only allows us to navigate a few hundred meters every day. But while this was okay for the last 20 years, this is the need and the requirements imposed on future concepts cannot work like this. Here are some examples of future mission concepts under development. And one of the key things that is differentiating from current existing rovers is that they would be from driving tens of kilometers in multiple years, we need to go hundreds of kilometers or more in a single year. So it's almost a 10x order of improvement that requires in how fast we can navigate. In order to understand why we move slow, let's take a quick look at a single slide introduction to how the current path planning system on the rover works. So this is a high-level overview of the ENAV algorithm. It basically consists of 3 parts, where you have a global planner that looks at orbital maps and tries to plan a long trajectory. A local planner, which basically makes sure you're kinodynamically okay, and you basically will not collide into obstacles. And for each path on that trajectory, what you would see is then it would do a safety check evaluation, which is done by our ACE algorithm. Now, this is the key computational bottleneck. Now, imagine you have a tree-based planner which has thousands of potential path options. And for each of those path options, you have tens or hundreds of safety evaluations that you do. You're now looking at a combinatorial problem where this becomes the computational bottleneck. And solving this can take several tens of seconds on the rover. So you basically the rover cannot drive till it makes this decision. So while Mars rover's driving algorithm ENAV has still been capable of driving us safely, it is definitely not as fast and it is not as intuitive. In contrast, human rover planners can do this in a much more intuitive and quick way. Just by looking at this image, most of you will be able to have a bias in terms of that you should not be going straight and take a right, slightly to the right of this rock. There is this perceptual capability that in our brain that allows us to do this. As opposed to that, the ENAV algorithm, it brute force evaluates each of the single trajectories, whether it is still, and without having any intuition into the plans. What we're doing in this project is, can we have, looking at the goal of, can we add this intuition to make our autonomous rover path planning quicker and more capable of finding paths in a complex terrain. So towards this effort, we've been using machine learning to basically learn this kind of planning intuition as a cost map over through past experiences. So the way we do this is we build very realistic high fidelity simulators of the Mars 2020 navigation algorithm, as well as simulate the environment. While it may not look photorealistic, it is emulating the kinematics and the dynamics, as well as the kind of terrain that you would encounter on Mars in a statistical nature. And through extensive Monte Carlo simulation, we can gather data on how the rover would be performing. And through that, we learn cost maps for the rover. And using that, what we observed was that we could get almost a three times increase in planning performance from a computational perspective. So over the last few years, we've developed, built, and tested these and integrated these algorithms into the Mars Perseverance rover. This is an image from the rover in the spacecraft assembly facility and clean room at JPL, where the rover was put together and brought to life. This is from earlier this year in January, just before the rover development was complete and packed up and sent to the Kennedy Space Center for launch to Mars. The rover was launched to Mars earlier this year, and it was a beautiful launch from Kennedy Space Center and a great feeling to see our algorithms that we have developed on its way currently to Mars. It's expected to land on the surface of Mars in February next year, and hopefully soon after that, we'll be able to see some of the developing in action. Looking forward, we have not just been developing navigation capabilities for our current rovers, but also having an eye towards future missions, which may have considerably different mobility systems. What you see in the images here are some concepts for future robots that we plan to send to Moon, Mars, and beyond. I'll give you I'll pick one of these here in the center where it's called the Lemur robot. And it's basically, think of it as a rock climbing robot. And the reason we're building something like this is because rovers cannot really go very close to cliffs. And if you talk to a geologist, the most interesting places where they look for signs and where they want to go and study do studies is actually on these rock cliffs. Think of the Grand Canyon. You basically get a single snapshot of the whole history of the planet. And that's what they want to do when they go to Mars. So we've been building robots like this that can actually climb on vertical walls and do science on them. We took our robots and we basically went to the site in New Mexico. It's an underground cave, which basically resembles similar underground caves that we expect on Moon, as you can see on the image on the right, top right. And the interesting thing about these environments is that they resemble the kind of environmental scenarios where humans could potentially survive. So basically, if you ever want to go to Moon or Mars and build a build a place where build a small colony, this would be one very big one place where I think it would be advantageous because of the temperature, protection from radiation, etc. So how does this fit in what I've been telling? So the Spock algorithm that we've been developing and the related machine learning technologies, we have been using that to also deploy these on these kinds of different mobility systems, just to see how adaptive these are to future rovers. This is an example of the perception system where we are classifying where the rover should be touching, holding, putting its graph so that it doesn't fall off. And here is a video of that being in action to actually climb. I'll move forward in the interest of time. And to the last slide, I'll just say that while I've talked about some of the navigation system that we've been building and how we've been using machine learning in that, one of the key things that gets me most excited is how some of these technologies can be enabled for human exploration. And that's something we are currently studying with the Artemis mission to going on taking humans back to the moon. And how can machine learning and AI be used for that? So in summary, machine learning has the potential to revolutionize robotic space exploration, in my opinion. I discussed some of the technologies under development for improving the autonomous navigation system. I presented some of the key technical challenges towards infusing machine learning into safety critical system. I'll let these questions be here and then take questions on, take any questions that you might have. Actually, I'll let these questions be here. So yeah. Thank you everyone for listening in and taking out time from your day to listening to what I have to say.
Great, thank you so much. That was really, really interesting. Lots of questions. Mark, as always, has leading the charge. So Mark asks, the physics of space and life in Mars are different from Earth. How big of a role will radio frequency wireless communication play in our pursuit to colonize Mars and enable ML in space?
Sorry, Stuart, can I ask you to again repeat that question? No. I was still capturing the screen. Yeah.
Let me try to say this. Sorry. I think he's essentially asking how big of a role will frequency wireless communications play in our pursuit of sort of enabling machine learning in space.
I'm not sure how the communication would. So if I understood the question correct, was if we improve the communication, does that do we still need autonomy and machine learning? I believe we do, because even though you can communicate faster, as I was saying, as you start going further away, it's not just about, you just cannot beat the barrier of speed of light. So it will still take hours to actually send a signal and get it back. And you just would want still these robots to be behaving autonomously in environments. So a classic example that we're currently studying is, imagine sending a robot billions of miles away to an underground ocean for a 20-day mission in Europa. So we are basically building a rover that could go there, land on the ice, dig down a kilometer down into the ocean, and just behave. So we have no idea how anything is there. So we don't just need machine learning for independent autonomy, but also for how can it be adaptive, because we just don't know anything about the environment.
Yeah, no, that makes a lot of sense. We don't know what we're going to see until we land there. Another one from Mark. Does the increased integration of systems on chip, SoC, ARM architecture with built-in GPU, have a huge impact on creating tiny ML algorithms that reduce computational energy consumption for longer rover exploration?
Yes, it has tremendous. And that's one of the main reasons we are getting fueled up to this. So I started at JPL around 4 or 5 years back, and it was at that point, it was just starting to, thankfully the timing was perfect, because we have seen a parallel growth in hardware, compute hardwares, and especially there. And this was an identified need for 2 to 3 decades. We've basically had computation limits on our systems, but now we are starting to get these system on chips, small systems that with enough compute that are also radiation hardened. A good example of that I did not present here is the Mars helicopter, which is going along with the Mars Perseverance rover. And it's actually carrying, its compute is basically a Snapdragon 820 processor, which is the same processor that you're using on your phone. Through partnerships with organizations like Qualcomm, we realized that it turns out that the processors they were building for phone are also radiation hardened just enough that they can survive the mission timelines that we need for the Mars helicopter. So I think those two things go really hand in hand, and we're hoping more of that happens.
Great, great. Another question here from Giacomo. I hope I'm pronouncing that correctly. Edge GPU solutions like the NVIDIA Jetson Nano cannot be used in space because they are not space hardened, but could they be helpful in an environment like Mars?
So that's, I think the same principles apply. So in terms of NVIDIA's Jetson, so we use those extensively here on Earth as an analog. But what I was saying with the Mars helicopter, I mean, so the Snapdragon 820, that was also never built for radiation hardened. It just turns out that even during regular development, they have been tested enough and they are still, they can work in some of those restricted environments. So maybe that is, it depends, it slightly depends on what your use case is. If you need it for long duration missions, if you need it for a very short mission, etc.
Great. I think that's the end of our questions, unless anyone else wants to type one in last minute. We are over time, but great engagement, 68 people. That's pretty, 67, somebody ran. Oh, everyone's leaving. Anyway, you did have pushing 70, which is great. So thank you so much for your time. Hopefully we'll see everyone in some of the workshops and closing off on the day. And Shreyansh, thank you so much for really insightful. Looking forward to seeing you on Mars.
Thank you so much, Stuart. This was great. And I see David. Thank you so much, David, for organizing the event.
Oh,
absolutely.
And, inviting me over.
David, apologies, David.
Absolutely.
I forgot you were going to pop in.
I just wanted
to so interesting.
I just want to come say hi. Shreyansh, that we had planned to have you in 2019 come and you had purchased your ticket and everything, and I really appreciate that. And we ran into some passport issues. So I just want to say hi, get a chance to meet face to face, and thank you again for joining. And hopefully, if things turn out in 2021, we can get you to come visit us here in Canada. Thank you so much.
Definitely. Thank you so much, David. Definitely, I look forward to that. And yeah, I'm very excited. And this was great. Thank you for organizing such a great event.
Absolutely. Take care, man.
Okay. Bye-bye.